we were at 3, so we had like 80 numbers.
Okay, so how did it go? Lots of you came for help. That's good. Good. And so, and then was that a rewarding challenge when you had to work at it and think about it? And
I felt okay. So the thing I had trouble with was getting where my labels where I wanted the math, because sometimes like the blue bar would be gone, but DZ would be like 0, and like is that even but I would think.
okay, well, so here's the great thing about GC. It does whatever mathematics you give it. So it forces you to have the math right. This is the beauty of this. It's not. There are some keystroke kinds of things you have to learn. And we're hopefully caught up on that. But basically, you put in the mathematics, and it will display whatever mathematics you put in. So that forces you to know it and be precise, right? Math is a precise language. It's not, as long as it's close, it should read my mind and graph it right. No, math is a precise language. You have to have it precisely correct, and then it will display it correctly. Okay. So I want to make sure, I forgot to mention this, but I want to make sure that everyone, you've got the thickness of the bars mathematically and not using the radius feature. So I did not want you to graph a line like the black line and then just crank up the radius to get the bars. So if you didn't create the bars, so you can have more time if you want. If you still don't feel like, if there's still revisions that you would like to do to fine tune it or maybe it doesn't work, you have more time. I won't make today's noon deadline. I won't make that strict. So if you want maybe like midnight tonight, would that be enough time for anyone who wants to do more work on it? All right, so I'll push that back to midnight tonight. Make sure that the bars are defined mathematically, not by using the radius feature. So then there was this thing I was showing you at the end of class, but it was too fast last time. The idea of efficiency. So there's displaying what you wanted to display, and then there's also doing that in the most efficient way. Okay, so for instance, the tick marks. Right, the tick marks. So if I open a new file, so if I want to, all right, say I want to put tick marks every 0.5, okay, starting from 0.5 up until 10, okay? So I don't have to do 20 command lines. I can do 20 command lines to put tick marks every 0.5, but I don't have to do that. So what I can do is, I can do one. Well, I was trying, that's what I tried to show you at the end of class last time. I know it was rushed, but I gave you an example of this at the end of class. So x equals what? So I can say x equals a because I want several different values of x equals. And then if I want to tick marks, what would be a good, how would I make these tick marks a good like height this way? What would be a decent height looking at the scale there? From what to what?
Probably go.
Anybody?
So like every.
Alyssa, go ahead. Okay, and how would I mathematically say that from negative 0.4 at the bottom to 0.4 at the top? What would I say? Good. Okay, but then I need to specify that I want the a value to take on many values, but not like variable, but like all of them at once. And so what you do is you do comma, and I can say a, and then control equals is a member of control equals, and then use the braces. So that's shift bracket, and then the first one I want at 0.5, and the next one I want where? At 1. Now I could make a list 20 long, or I can establish a pattern and do ellipses. So you could do control semicolon, And that means continue this way until, I think I said 10. So that will, what will that do? That will graph every single a value at once. X equals all those a values, and then y from negative 0.4 to 4.4, and that should do it. So this is a nice technique if you want to, if you're repeating something over and over again, and like another, we can use that for like the unit circle. I could say, first of all, if I could say r equals, so r is reserved for the r variable in polar coordinates. So if I say r equals 4, that'll just graph the circles 4. And now say I want to do radial lines every pi over 8 or pi over 12, say. Yeah, every pi over 12. So I can say theta equals b. And if I want them every b is a member of, so pi over 12, comma, what's the next one? Pi over 6, comma, ellipses, control, colon, comma, all the way to 2 pi. And then I want that from r from 0 to 4, because that's the radius of the circle I made. Let's not do green. Let's do blue. Let's say black is fine, or gray. So what will that do? Do you see what that will do? Make a pie, right? Make a pizza. But why doesn't it go all the way? Because here r is showing, what does that say? 2. So I got to change that r value here. There we go, got it. Did gray show up? What's that? I think I changed to 4. Did it say 4 or 24? Oh, but then so yeah, it's a 24, but then I restricted it here. So, you know, if I would have done 1, but I could take this, if I have 0 to 4 here, I could have taken this off. I could have taken this off and made that 0 to 4, and then it would be the same effect. Okay, but the point is, again, great way to kill lots of birds with one stone, right? You have one command line to do that. So please take note of that construct. That might come in handy. Yeah.
With the number labels too, is there a way to be more efficient in that, or is that just?
If you have a PC, the labeling is really clunky and very restrictive.
So
the labeling is a lot nicer in Mac. If you have Mac, and you can even drag and drop text, it's very nice. So you can just, usually you can. I don't know, sometimes you can, sometimes, I don't know why sometimes you can, sometimes you can't. Usually you're able to drag and drop. Maybe it's too long, or spaces aren't allowed or something. There we go. No, I don't know why. So this was a drag and drop. I think these were drag and drop as well. But yeah, the symbol, you're kind of restricted to symbol, and you're not allowed spaces. And then if your thing is too long, then it crashes. So it's really putting the nice labels and titles and descriptors with PC version of GC is just not. It's not convenient and efficient. So sorry about that. But if you have Mac, anyone have Mac? Yeah, then the labeling is a lot cleaner. And does drag and drop work for you? Have you tried that? Drag and drop. Yeah, it usually works for me. I don't know why it wasn't working. Okay, any other questions about the project? So then once you get it working, then you want to fine tune it so it looks tight, it looks nice, so you notice how mine, yeah, the things are where they should be, and it looks nice. And that, that has some value, especially if you're using it as a didactic object. If your Z is way up high, it's just a little distracting if you're, talking about values of Z changing. So think about, once you get all the math right and it works properly, then go back aesthetically and make it look like as professional as you can. That would be, so just for using it as a teaching tool, there's no distractions in it because there's some weirdness to the way things are positioned. Okay. Yeah.
So, okay, I guess I was confused as talking about how it's to get the bars to move. DZ should be able to grow on its own, right? And then
In the second view, right?
yeah.
Yep. Are you talking about the second view?
Yes.
So then in the second view, at n equals 0, dz is just nothing, and then it grows with z until it comes to its full value. So now dz has its full value when n equals 1, and it shows up. Does that help? Yeah, that's what you want for the second view. Okay, other questions? Did you bring your handout from Thursday? One of you did? So if not, you should probably be able to do it on a blank paper, but the handout will be helpful if you have your handout from Thursday. That's it. So we had worked through this, right? So the next couple of weeks, we're going to be working on this endeavor, which is pretty much half of calculus. You know how fast something is changing at every moment. You want to know how much of it you have at every moment. And so what is the how fast something is changing? What is that? How do we know how fast something is changing at every moment? Where does that come from? Rate of change, specifically, what about at every moment? Doesn't have to be constant, but you know how fast something is changing at every moment implies rate of change, a function, right? Not just a rate of change, but a function, right? So that at any moment, it's telling you what the rate of change is, and you want to know how much of it you have. What is that? Accumulation.
Net accumulation
Function, right? Net accumulation function. And so we said this was our rate of change function. This was the easiest kind, a constant rate function, like the water filling up the tub at a steady rate, right? A steady rate. And then from that, we can get a net accumulation function, which tracks the amount of change, or the amount of variation from a starting point. And then a total accumulation function. So both of these are versions of how much you have at every moment. Okay? Maybe the total accumulation is like truly the how much you have at every moment. But a net accumulation function is certainly, it's close brother or sister, okay? All right, so this is what we're after. So here's a new situation. The function R sub V gives the rate of change of volume of oil expelled per day by a rig that begins leaking at t equals 0 days. So did I give you that on the worksheet? Okay, so on the other side, what does it show? Just that graph. Okay, so you want to, yeah, I think you'll have room if you just maybe up in the upper right-hand corner. So if you want to try, what would the function v that gives the total amount of oil expelled x day after the rig started to leak? So if this was the rate of change function, can we just get a rough sketch of what the accumulation of volume function would look like? Can you do that? You per day, but all right. So I think most of you got it. This looks something like this. Always increasing. Why is it always increasing?
Because it's positive.
Rate's always positive. So even down here, we're still expelling oil into the ocean, but just at the lowest rate, right? Okay, so our goal is then actually precisely define the function v. Okay, actually define precisely the function v given the rate function. Okay, what makes this challenging? What's that? Oh no, we will have the rate function. Yeah, we have it. So we're given this RV. I can give you the formula, but we'll have it. We'll have it. But compared to like the bathtub filling up, what makes this challenging? Bathtub was simple. You just sketch the net accumulation and total accumulation functions like that. Not constant rate of change, right? We have a changing rate of change. This is the challenge to this. With a constant rate of change, boom! It's so easy to know what the net accumulation or total accumulation is. But with a changing rate, this is much more challenging. Okay. All right. So we're going to still do it though. Okay, so let's ask this question. How does the statement R sub v 0.79.68 relate to the graph? So we're not interpreting the numbers yet, but how does that statement relate to the graph? What do you think?
Given a small change in time at 0.7 days, the corresponding change in the volume of oil will be 9.68 times that change.
Is that what you're going to say, Veronica?
Yes.
Yeah, exactly, right? Exactly. At the moment, 0.7 days. Okay. Let's see. But so what does that mean? So yes, that's true. Jason, that's true. That's what you said. But then I was continuing to ask the question: what does the 9.68 meters cubed per day mean? Given a small change around 0.7 days, change in days, the amount of oil leaked would be 9.68 times as much as that change in days. Or what's our formula? Okay, so what do we say? The meaning of that 9.68 is that? What could we write? So what's the mathematical statement behind what she said, or the mathematical statement that describes what Alyssa said?
That in this moment of 0.7, that if you like look into it,
I'm looking for a mathematical statement. Mathematical statement. What would that be? Right. Times. Okay, so we have to have this on our fingertips, right? Whenever we have a rate of change, we have to be thinking this. So, is this true for any change in time? Why not? The rates change immediately, right? So as soon as you get away from 0.7 days, you have a new rate. So how can we say this? How can we still say this? How can we still use the fact that dV equals 9.68 dt if, given the change in time, the rate will change? right, so what about dt? What would dt have to be like?
From 696 to 0.73.
Small, right? In the moment. Yeah, so in the moment. So I'm showing a moment here, right? I'm showing a moment. And so then dt, if dt varies within that moment, then we can say dv is essentially, or the rate is essentially constant, and dv equals 9.68 dt. Okay, so then how would I then kind of change this graph? How would this graph change to reflect that? That in the moment, we're saying that the rate is essentially constant at 9.68. Then that graph doesn't really reflect that anymore, right? So what would the graph be like to reflect that we're saying in the moment the rate stays essentially constant at 9.68? What's that? Horizontal line, right? Horizontal line, right? So we're thinking about in this moment that the rate is constant at 9.68. So the rate of change at the moment of t.7 days is constant at 9.68. So that's how kind of we're thinking about it, even though the rate is changing. Okay. Okay. So now we're going to suppose I'm telling you that the volume at 0.7 is 13.15 meters cubed. Okay. So what is that, Veronica? What is that? What is that? What is dx? 0.002. You guys agree? Alyssa, Jason agrees. Yep. 0.002. Good. Okay. And then what about dv? So you don't have to do anything in your head. You can write out. If you want to have it be an expression, that's fine.
Would there be two ways of representing this? Is that, or are we going to do it like the MDX?
We need to find the number. So we can't. There's only one way to get it to find the number. So Lydia, what do you think? dv. So
Yeah, I would like to say like 13.15 plus m times 0.002.
that's what dv is?
Yeah.
dv. You're trying to find v of 0.7. It sounds like you're trying to find v of 0.702. I'm just asking for a dv.
Okay, then d of 0.702
But we're gonna use dx and dv to find it. So we can't write dv in terms of v of 0.702 because we need to, right? So you had it. It's just you had it as part of what you said before.
Oh, I meant d of 0.702.
Okay, but we're trying to find this, so it can't be part of the things that we're using to find it, right? So we need to get dv apart from v of 0.702 because we're trying to find v of 0.702. Does that make sense? So it's not gonna have anything to do with v of 0.702 because we're gonna use it to find that. So Veronica, what were you gonna say?
I was gonna say d of 0.7 plus
No, it's just dv, guys. Dv. This is constant rate of change. dv equals 9.68 times dx. Yeah, Jason said that. Yeah. So this is we're at 0.7, right? This is at the 0.7. Yes, this is the same problem from before. Sorry if that wasn't clear. Because we're at right v of 0.7, and then we have our rate of change at 0.7, which is a 9.68. Okay. Note to self for next year. Okay, so now what? Now I want to find v of 0.702. So this is familiar. We've done this before. This is like v final. How do we find v final? V initial plus dv, which is mdx. That's right. Okay. And so let's we're gonna show this whole thing down here, right? So at 0.7, where should I plot a point? Is that here? I'm in the right intersection? Cool. And then so how am I going to show dx? How do I show the dx? And where do I stop? Is that right there? So there's my dx of 0.002. And then did anyone find this value? What is this value? Because I want to make my picture look right.
Yeah, it's basically 0.02.
0.02?
Yeah.
Okay, so I'm going to go, how high will I go? Is that all the way up to 0.17 there? Is that right there? So here's my dv, and that's mdx, and that is 0.02. So now I can write so what are the coordinates at this point? So the coordinates at this point are? That was the given, right? The given volume at that time. And so now I can write this one, and let's write it as an expression. So x coordinate as an expression, what would that be? The x coordinate is? 0.7 plus 0.002. Right, and that's our 0.072, that's what we wanted, right? Or 0.702, comma. Yep, and so let's break that down there. Where did that come from? That came from 13.15, the initial, plus the 0.02 mdx, which gives 13.17. So there's initial x plus dx, initial y plus dy, which we found by constant rate of change, mdx. So this is very familiar, right? This is the exact same way we did what? What were we working on when we did all the same stuff? We did this before? A couple weeks ago? That was for finding what? Linear relationship, right? Linear relationship. And so we could do that same thing for any value in here, right? So any point on here, we could go through that same process, and then we would be defining, so what would that be? So what would the x coordinate of that be? 0.7 plus dx, right? And the y coordinate? 13.15 plus 9.68 times dx. What's the y-coordinate? Or that would equal what? V of?
Or
0.7 plus dx would be that y-coordinate. And so, in essence, by writing this, what have we written? 13.15 plus 9.68 times. Let's write that a different way in terms of x or time. Are we using t or x? What are we using here? We're using x, okay? So if I want to write that in terms of x, what would it be? X minus 0.7, good. So how much oil is it? Is it, first of all, is it an amount of oil, or is it a number of days, or is it rate of change? What is that thing in the box? Amount of oil, right? V final, right? So now, is it the amount of oil that leaked in the moment, or is it a different amount of oil?
the total amount of oil.
What do you think, Alyssa? Total amount of oil since when? Since x equals 0. So is it the oil that leaked in the moment, or is it all the oil leaked since 0? So
wouldn't it be since 0 since we're adding what's already
yes, right? So we start with all the oil accumulated up to 0.7. That's the 13.15. And then this is, what is this amount here? That's our dV, right? This is V initial plus dV. So what's dV? How much oil is that? It's this amount of oil, right? This is dV. Right? So that's how much oil has leaked over the dx, right? So in the dx amount of time, that's how much oil has leaked in just the dx, plus all the oil that leaked before. So you know how fast something is changing at every moment? You want to know how much you have. So haven't we constructed how much we have? But what's the problem with this? So yes, absolutely. We know how much we have, but we only know how much we have when? In the moment of 0.7. So I want to know over 2 days. So I want to know how much I have at every moment over 2 days. So how many times would we have to do this? How many moments are there in 2 days? A lot of moments, right? So this is great because now we answer the question, how much do we have? But only at one moment, not at every moment, right? Okay, so how are we going to do this? So the question is, we want to come up with a function like this that gives us how much the volume of oil that's leaked in the ocean at every moment, not just one that works in a particular moment. Okay, so this is awesome, and it uses a lot of stuff that we need, but this approach will take way too long because we've got to do this for every single moment, right? Okay, so let's take a different tact so we can talk about how do we get it a function for every moment, not just one moment. All right, any questions on this? So it should feel like review of what we did with the linear function stuff, but now it's just all in a moment, right? It's all in this small amount of time. Yeah.
Is this video going to go on the canvas?
Yeah, I'll put this one up. I know I haven't been good about that, but I am recording, and I will definitely post this. Okay. So we need a new strategy, and here's what we're going to do. So we're going to look at. Oh, all right. We can skip this. We can skip this. So this is basically talking about how dv equals mdt is kind of the heartbeat of this whole question, because we know the rate, right? Given a constant rate, we can calculate a little bit of accumulation, and then we can use that to build up a net or total accumulation. So this is just underscoring, this slide just underscores that dv equals mdt is kind of the whole heartbeat of this problem. You know how fast something's changing, you want to know how much you have, because you know how fast it's changing. Little amounts dv are what we build to create the function, how much of it you have at every moment, or the accumulation function. Okay. All right, so how are we going to do it for every moment, not just one moment? So here's what we're going to do. We're going to pick off at regular intervals. We're going to get rates at regular intervals here. So I think I'm doing it, is this every 0.4? So I'm highlighting points every 0.4 days, and then I'm writing what the rate of change in that moment would be. So I'm writing it first as in function notation, and then approximating it. So how is it that the rate of change of oil being spelled at 0.4 is 17? How is it that the rate of change is being approximated there as 17? How is that? Yeah. Right, so the rate of change graph means that the rate of changes are y values on the graph. So how about 0.6? So tell me, if I were to have the 0.6, I want you to represent it. So represent that point with an ordered pair, and then estimate the value of the rate. Okay, right there. Can I just? So you guys do that just for practice, because I've already done these for you. So. There. So right where the arrow tip is, I want you to write that as an ordered pair, exact values, right? Exact values as an ordered pair, and then estimate the rate. Okay, Alyssa, did you get this? Yeah.
0.6 and the rate of volume is 0.6, and then I said quantitatively like 11.
So is this is what the ordered pair you have? Okay, and then you say that that is approximately 11. What do you guys think? Agree? You disagree with that? Why?
Or well, if we're doing it by like approximate, wouldn't the rate be with what like the left end was, which was 17?
No, I'm asking about this point right here. I'm asking to do the same things that we did with these points with that point right there. About 11. So we get everyone in agreement on this? Okay, so I just wanted you to practice doing one yourself to see where all these came from, right? So the x value and then the rate at that x value or number of days, and then those rates we can kind of approximate them by the y value on the graph, because this is a rate function. Okay, so what are we going to do now? So in order to kind of try to do the whole function at once, we want to leverage what we know about constant rate of change. So in every interval, we're going to, so here's in that first interval from 0 to 0.4, we're going to say that the rate is constant rather than changing. We'll say it's constant at RV of 0, or approximately 28. And then in the next interval from 0.4 to 0.8, we'll say that the rate is constant at RV of 0.4, or approximately 17, and then the same with everyone. So to get around, so what we're doing, to get around this fact that the rate is changing, let's make it into constant rates, right? So with constant rates, we can use dv equals mdx. And we got easy math to do that. And we don't have to worry about the gradually changing rate anymore. Okay, but what's the downside? It's an estimate. And how is this blue rate function compared to the nice, perfect, exact red rate function? Is it good, or does it do a good job?
It's okay.
No, really, it's not great. It's okay, but not great. Like, for instance, in the first interval, how does our new rate function compare to the actual? Is it close or no? Way too high, right? It's way too high the whole way. So advantage, it's constant. We can easy math, right? Disadvantage, it's not accurate, right? It's way too high for most of the interval. Now, down here, this is pretty nice, right? So this is what, fourth interval? That constant rate does a pretty good job of mimicking the function, but that's just because the actual function levels out. All right, so our new function is created from the exact rate, RV, and it approximates the function RV. And we're going to call this just R. So R, just R by itself, is the approximate rate of change function, which we're going to use to build accumulation. But we're keeping in mind that it's not the exact rate function, right? It's approximate, so it can only give us approximations. Okay, so what is R of 0.5? What is R of 0.5? Exactly and approximately. What is R of 0.5? So exactly, what would you say? So listen. How could you express what's R of 0.5 exactly? So is R of 0.5 the same as R of V of 0.5? Is that right? What's RV of 0.5? Isn't that for this point here? Doesn't that point give us RV of 0.5? Is that R of 0.5? What is R of 0.5?
Would R of 0.5 be the approximate? Right.
R sub V is the red graph. It's the exact rate function. R is this new function of constant rates, the blue one. So I want R of 0.5. So I want it exactly first and then an approximation. So an exact, how can we say what R of 0.5 is exactly? You want to change? No, because RV of 0.5 is down here on the red, right? That's RV. That's RV of 0.5. But R, these are the points on R. R is this step function of constant rates. That's the R function. So R of 0.5 is? RV of 0.4, right? Yeah, good. So is that what you're going to say? What is R?
Oh, I was doing it approximately, sorry.
Okay, so R, exactly, R of 0.5 is?
R of B.
RV of 0.4. RV of 0.4. And approximately, R of 0.5 is?
So RV is 0 plus RV is 0.4 plus per time. I don't know.
It's the same approximation we had for RV of 0.4 before. So if R of 0.5 is RV of 0.4, then it's the approximate value of R of 0.5 is the approximate value of RV of 0.4. So that is 17, right? 17. All right, what's R of 0.9? What's that? RV of 0.8, and that's approximately 8. Lydia, what's R of 0.2? RV of 0, and it's approximately? Right. So that's exact, and it's approximately 28. Yeah, so what happens is the rates that we get for this approximate rate function is the exact rate at the start of the interval, right? It's always any rate that we have for this new blue function, this R function, is always the same as the exact rate from RV at the start of that whatever interval we're in. Make sense? Cool. All right, so now we want to write this. I want to write this function. And so that we're going to write it piecewise, right? We're going to write this thing piecewise, which means we're going to have our first piece. What are the x values for our first piece? It's the x. We'll do the ranges first, and then we'll do the pieces. So 0.4. And then? Right. And then? Six. Okay. And so then what is the values of R when x is 0 to 0.4? Exactly. RV of? Good. And then in the second interval? Right, right. So in every interval, this new function R with these constant rates, every rate is what? The rate, the actual rate, the real rate at the start of the interval. This one is? Are we good on that? So that's just mathematically, that's the definition of the function that I graphed, that I showed you in blue. That's the blue rate function. So now we want to write the corresponding accumulation function using this, right? So I've got constant rates in every interval. I know how to write my accumulation at constant rates, right? What's the general form of accumulation at a constant rate? What's the general? So what's going to be the structure of this? So of every piece. So again, we're going to go from 0. Okay, so accumulation is values of accumulation function are, what are they in general? They're values of, in this case, volume. So how are we going to get values of volume if we have constant rates? Okay, does that give me values of accumulation, or what does that give me values of if I do m dx? Yes, say it louder. Right, so the general structure of that is, put it all together then, the general structure is to get values of accumulation. Previous, what's the change? Y final equals Y initial plus change. So that's what we'll have every time. We're going to have all the previous accumulation plus the change in the current interval up to x. All right, so what's in this first one? What's all the previous accumulated volume? 0 plus? Okay, so we want to use our approximate rate. So we're going to use so we could do r of 0, but because it's constant, we can make it r of x, right? And then r of x will be rv of 0 for that whole interval. Is that right? Okay, times? So initial plus m dx. And what's dx in terms of x? X minus 0, right? Change in x in that, right? So that's our dx. So x minus 0 is dx times the rate in that interval, the constant rate rx, plus all the accumulated volume from before. Okay, and then next interval. How much do we start with? Is that the accumulated volume, 0.4?
Wouldn't you start with that whole thing that you got at the top? Or like the first equation? So wouldn't it be
But this was a function of x. This was a function of every x value in that interval. So let's sketch that. What is the rate? About what? 25? 24? What does that say? 28. 28. All right, so this is really like the function, what? 28x. So when we get to 0.4, where will we be at? 0.4 times 28. What's 0.4 times 28? Anyone got it? Like 13, 12? 11.2. I think that's right here. Is that right there? And so how am I going to draw the graph in this first interval? What will it look like? Straight line, right? This is constant rate of change. It's going to give a linear accumulation, right? So now I'm going on to the next interval, and so the structure is going to be of this accumulation. What's the structure? Fast. Here we go. Structure is
28 plus
28 was the previous rate.
accumulation, so it's going to be 11.2 plus
Okay. So yeah, all the accumulation in this first interval plus.
r of x
Yep.
times x minus 0.4.
Yep. Now, how can I represent all the accumulation from the previous interval? Exactly. What is it? That's the rate.
What did you do? A of
Remember your piecewise project? Jason, what do you want to do?
A of
Can we do A of 0.4 here? Because that's all the accumulation in the previous interval. And were you wondering why I was doing less than on this side and less than or equal to on this side? Did anyone think about that? No? Did they notice that? Well, that's because of this. I want to have less than or equal to on the right side so that I can use x equals 0.4 and do A of 0.4. All right, let's graph it. So what is this rate now? This rate was 17. What's 17 times 0.4? 6.8. And so at 0.8, where will I be? $6.8. Will I be here?
6.8
Plus the 11.2, right? It's all the 11.2 plus the new total amount accumulated in this interval, 6.8. What is that? 18? What are we doing? So in essence, what are we doing? Right, of oil, right? So this is that we're creating a volume of oil function. Is it exact or approximate? Based on the blue rate function, so it's approximate. Next one. So next will be everything we've gotten up to 0.8, which is our 18, right? Plus? Which one is it? Yeah, it's going to be dx in this interval, right? So it'll be x minus the starting x of this interval. So that's the dx minus 0.8. Okay, and quickly, so what's that? 8 times 0.4 is 3.2 plus the 18 is 21.2 at 1.2, 21.2. It's hard for me to see on the lines there. Is it right there? Something like that? Tell me, Veronica, what's making more sense? Everything. Okay, good. So then in the next one, we'll do one more. All the accumulation up to 1.2, which is our, what, 21.2? Is that right? Plus, at the new rate, so R of x, m dx. And so then this will flatten out a little bit more. Something like that. Does that kind of look like the one we sketched at the beginning? Yeah, it's got the general flavor of that accumulation function we tried to sketch from the red one, right? Okay, so you know how fast something is changing at every moment. In this case, oil being spilled into the ocean. You want to know how much of it you have. So we're building a approximate version of that. One linear piece at a time, right? For each constant rate, you have a linear piece. Takes all the accumulation from before and then grows steadily at the new constant rate. And then again, takes everything from before, grows steadily at the new constant rate, takes everything from before, etc. So volume final equals volume initial in that interval plus the change of volume in that interval. What about the y-intercepts of these lines? Relevant? No relevance, right? No relevance. mx plus b is not helpful at all because the y-intercept of this, who cares, right? Y-intercept of this line, who cares? So this is doing great work for us. Everything from before, y previous plus the change in y. Okay, let me show you the next project. It's based on this. Any questions? All right, cool. So here is, it's down here. All right, here it is. So it's based on, this is still the oil slick. So over here, I can, what's going on? Oh, here. So this is that same rate function, okay, for the oil. And then up here, this A slider lets me choose a starting value of A, okay? And it can be any starting value of A. Okay, so like here's the starting value of A of like 0.35. And then when you change the N slider, it will kind of proceed through dx in that for that interval of 0.5. And as it does that, over on the right, it's going to build like the net accumulation starting from that value up. So notice, what's the rate here? It's about 19 or 18. Okay, so now if I come here and make A where the rate is much lower, then when I change N, notice what the graph looks like. It shows the accumulation at that lower rate. Okay, so the starting value of accumulated volume is going to always be 0.3. We're just going to like leave that out of it. So you can always have it. So notice as I change A, your starting value of accumulation will always be 0.3. So we're just kind of leaving that aspect out. But you need to show as n increases, that's like dx, right? That's like increasing dx. Show this amount of accumulation, which is accumulating at this rate, at the value, the x value A over here. And then one more thing you have to do is your file will not have question marks here. Your file will have the appropriate variables and parameters replacing the question marks. So 4 single question marks, 2 over here, and then these ordered pairs. Okay? So you're going to be putting in symbols and expressions in for those question marks that are correct and appropriate. Okay.